This is sections 9.7 and 9.8 of Honors Algebra 2, Quadratic Systems. So we've seen systems of linear equations, where we use substitution or elimination, linear combination, to solve them. Well, now we've got quadratic systems. Quadratic systems are systems of quadratic equations, so equations where the variables are squared, or maybe some linear equations thrown in there too, like maybe a quadratic equation and a linear equation. How many solutions will these systems have? Well, however many points of intersection the graphs have. So I've got three examples here. The one on the left, that blue line, which is x minus 2y plus 2 equals 0, and that hyperbola in red, x squared minus y squared equals 4, that system of equations has two solutions. The 2 points where those two graphs intersect. Right there and right there. Okay? The second one, x squared plus 4y squared equals 25, which is an ellipse, the one in red, and then 3x plus 8y equals 25, which is the line in blue. That line happens to only touch the ellipse at one point. It is tangent to the ellipse, so there is one solution. If, say, the line was just a fraction of an inch lower than that, it would intersect the ellipse in two places. If it was a fraction of an inch higher than that, it would not intersect the ellipse at all, and there would be no solutions. And the one on the right, I've got a red parabola, x squared plus 5y equals 15, and a line, x plus 2y equals 8, and they don't intersect anywhere. But again, if my line was a little bit lower, it might intersect in two places. If it happened to lie exactly tangent on the parabola, it would intersect only one place. So there are a whole bunch of different options. And maybe I'd have two hyperbolas. Maybe those two hyperbolas intersect in 4 different places. So I could have 4 solutions. So it all just depends on what you're graphing and what the situation is. So we'll do a couple of examples. Graph and determine the number of real solutions. So I've got 25x squared plus 4y squared equals 100, and then 5x equals, graph each of them separately. So let's take 25x squared plus 4y squared equals 100. If I divide both sides by 100, I'll notice that I have an ellipse, x squared over 4 plus y squared over 25 equals 1. An ellipse where a is 5 and b is 2. And it's going to be vertical. So my ellipse, just sketching this real quick, it's centered at 0, 0, and it looks like that. There's my ellipse. Cool. The second one, 5x equals y squared minus 15. Since the y is squared and the x is not, this has to be a parabola. So let's make it look like a parabola. I'll bring the 15 to the left-hand side. I'll factor out the 5 over here, get x plus 3 equals y squared. I'll divide both sides by 5, get x plus 3 equals 1/5 y squared. That's a parabola with a vertex at negative 3, 0. I'll do this one in green or red. Let's go with red. Vertex at negative 3, 0. And then if I just pick another point, let's say I pick y to be 5, then y squared is 25 divided by 5 is 5, and then I'll subtract 3, and I'll get 2. When y is 5, x is 2. Y is 5 when x is 2, and then I've got symmetry down at negative 5 as well. Okay, so there's my parabola. How many points of intersection do I have? Well, I've got 4 of them. 1, 2, 3, 4. So how many solutions will the system have? It will have 4 unique, distinct, real solutions. Example number 2. X squared plus 6y equals 30, and xy plus 6 equals 0. Let's start with x squared plus 6y equals 30. What kind of a conic is that? That's a parabola, since the x is squared but the y is not. So let's make it look like a parabola. X squared equals negative 6y plus 30. We'll factor out the negative 6 on the right-hand side. Make it y minus 5. We'll divide by negative 6 and make it negative 1/6 x squared equals y minus 5. That's a parabola with a vertex at 0, 5. Right there. It's got to open down. And if I just pick another point, like maybe I'll take x to be 6, then I'll have 6 squared is 36 divided by 6 is 6. That's a negative 6. I'll add the 5 over, so I'll have negative 1. When x is 6, y is negative 1. And when x is negative 6, y is negative 1. Okay, and then I will draw my parabola. Now the other graph, xy plus 6 equals 0, I haven't really graphed anything like that before, but we can notice this is equivalent to saying that y equals negative 6 over x. So I can just plot points. And if I were to do that, and I'll save time by not doing that right now, it would look something like this. It would have two pieces. It would look like something like that. And it's going to have 3 points of intersection. 2 up on the top left there and 1 down on the bottom right. So that would have 3 real solutions. So, okay, Mr. Shaver, how do I actually find the solutions? Great question, Chris. Well, we will use substitution or linear combination, just like we did when we had systems of linear equations. So let's tackle this one. 4x squared plus y squared equals 25. That looks like it's going to be an ellipse. And 2x plus y equals negative 1. That looks like it's going to be a line. Okay? So I could have 0 solutions or 1 solution or 2 solutions. We'll see what we get. So let's say I take the line, and let's solve that for y. So y would be negative 2x minus 1. We could substitute that into the first equation for y. 4x squared plus, and I'll take negative 2x minus 1, and I'll square the whole thing, and that equals 25. Now squaring that whole thing means I'm going to FOIL it out. So I've got 4x squared plus negative 2x quantity squared is positive 4x squared. Okay, then I'll have positive 4x and then a positive 1, and that equals 25. So 4x squared plus 4x squared makes 8x squared plus 4x minus 24 equals 0. I'll divide everything by 4 to make it simpler, and I'll get 2x squared plus x minus 6 equals 0. And I can factor that, and it factors nicely as 2x minus 3 times x plus 2, which means x equals 3 over 2, or x equals negative 2. But remember, I'm not done there. I have to find the y values that go with each of those. So I'll substitute 3 over 2 in, and I'll find y that goes with that. And I'll substitute negative 2 in, and I'll find the y that goes with that. So when x equals 3 over 2, I'll have y equals negative 2 times 3 over 2 minus 1. So y then would be negative 3 minus 1, which is negative 4. So I know the point 3 halves comma negative 4 is a solution. But what if x equals negative 2? Then y would equal negative 2 times negative 2 minus 1, which would be positive 4 minus 1, which would be 3. So I know another solution is the point negative 2 comma 3. Because when x was negative 2, I got 3 for y. So I have 2 solutions, and I will write them as a solution set in braces like that with a comma in between them. And each of those solutions is a point, so they need to be written as an ordered pair. So that's the way I write my answer. So this time, my ellipse and my line intersected in 2 places. My line must cut straight through my ellipse. Number 4. X squared minus y squared equals 12. Xy equals 8. So x squared minus y squared equals 12. Let's take the other one. Xy equals 8, and let's view that as y equals 8 over x. I can just divide both sides by x, and y equals 8 over x. So I'll take x squared minus y squared equals 12, and I will substitute in 8 over x for y. Okay? So that means x squared minus 64 over x squared equals 12. And then I'll multiply everything by x squared in order to get rid of my fraction on the left and on the right. That means I'll have x to the 4th minus 64 equals 12x squared. If I move everything to one side and the 0 on the other side, x to the 4th minus 12x squared minus 64 equals 0. And this is an equation in quadratic form. Remember, we know how to solve this as long as we treat x squared as our variable, essentially. And this will factor nicely with an x squared there and an x squared there. Here, there's an x squared there, an x squared everywhere, an x squared. Then you've got negative 16 and positive 4. Because negative 16 times 4 would make negative 64, and negative 16 plus 4 would make negative 12. It works out like that. And then notice x squared minus 16 is factorable itself as x minus 4 times x plus 4. X squared plus 4 is not factorable over the real numbers. Since we're looking at solutions as points of intersection, we don't need the complex solutions. We're only really looking for the real solutions here in this section. So we'll have x minus 4 equals 0, or x plus 4 equals 0, or x squared plus 4 equals 0. If x minus 4 equals 0, that means x equals 4. So if y equals 8 over 4, then y equals 2. So I'll have the point 4 comma 2 as a solution. If x plus 4 equals 0, then that means x equals negative 4. And if y is 8 over negative 4, that makes y negative 2. So I will have the point negative 4, negative 2 as a solution. If x squared plus 4 equals 0, that means x squared equals negative 4. And if I try to take the square root of both sides, I'll have the square root of a negative number. And again, I'm going to ignore the complex, the imaginary solutions, because they do not lead to points of intersection on my graph. I have only two solutions here, 4 comma 2 and negative 4 comma negative 2. And I write them as a solution set. And last example, number 5. X squared plus 2y squared equals 23, and 2x squared minus y squared equals 1. Okay? Let's take, say, so I've been using the substitution method. Remember, there's another method, linear combination, and that will work here. If I were to take the second equation, and I were to multiply that by 2, all the way through, I'll end up with 4x squared minus 2y squared equals 2. Notice that if I add that to the first equation, my y terms will cancel out. So I multiply by 2 so that I would have the same coefficient. I can only do that because my variables have the same powers here. If they were not like terms like that, I wouldn't be able to multiply by something in order to cancel them. So this works as long as my variables create like terms for me. So I'll add these together. I'll get 5x squared. The y's cancel, and I'll get 25. That's convenient. That means x squared equals 5. So x equals plus or minus the square root of 5. So remember, that's two possibilities. It's the positive square root of 5 or the negative square root of 5. I need to find the y values that go with each one. Okay? So if we take one of our two equations, it doesn't matter which one, I'll take the first one, and I plug in square root of 5, the positive value, positive square root of 5. I'll have to square that. That'll give me 5. Then plus 2y squared equals 23. Subtract the 5 to the other side. Then 2y squared equals 18. Divide both sides by 2. Y squared equals 9. It means y equals plus or minus 3. So when x is positive square root of 5, I get two values for y. So that's going to lead to two separate solutions. Square root of 5, comma 3, and square root of 5, comma negative 3. But what if x is negative square root of 5? Well, notice nothing else will change, because when I square it, I'll still get positive 5, so I'll still get plus or minus 3. Okay? That leaves me with two more solutions. Negative square root of 5 also gives me a y value of 3, and negative square root of 5 gives me a y value of negative 3. So I've got 4 points of intersection. This is an ellipse and a hyperbola, and they're going to intersect in 4 different places. So I have 4 points of intersection. Here are your immediate practice problems. Number 1, graph the system and determine the number of real solutions. X squared plus y squared equals 16, and y plus 2x squared equals 0. So that's a circle and a parabola. Graph them, determine the number of real solutions. Number 2, solve the system. X squared minus 9y squared equals 9, and x plus 6y equals 3. So solve it using the substitution method. That is the end of sections 9.7 and 9.8.